Hi, my name is Donnya Ajdari, and my group members are George Alexopoulos, Jon Garret, Robert Kantlehner, Janani Ramakrishnan, and we're going to be going over the filter block of the analog system design project. So as a basic overview, we are going over the neural recording application, and here we see the front-end system design on the left. You can see that there's an input signal that goes through an LNA and the filtering process, which is what we'll be doing. On the right, you'll see a more expanded version of this process with two lines, including a bandpass filter and a low-pass filter with the specifications for each filter on the bottom. After the signal has gone through the filters, they go to the ADCs. And we want minimal power in this application. So here we'll be going over the filter stages and parameters. As seen in the previous slide, there were two paths, the bandpass and the low pass. For the bandpass, we use this to identify action potentials, and we use this to allow frequencies above 10 Hz. The second path of the low pass is for identifying low frequency wave going through the neural tissue, which is frequencies of 5 Hz and below. And down in the second table, we'll see the parameters of Vout, Vin, the power supply rails, and the distortion, which we'll be measuring using the two-tone test, as well as the signal-to-noise ratio. Here we see the overall design schematic in Multisim. The top section here is the first path of the bandpass. You'll see that there are three bandpass second-order filters cascaded together, as well as a gain term at the end. And on the bottom here, you'll see two low-pass sections. One is a first-order low-pass, and the other is a second-order low-pass. All of these are biased with a bootstrap.
So for the first path, we used a bandpass filter with the following requirements. You use a pass band from 10 Hz to 4 kHz with a 1 dB ripple, and a stop band at less than 5 Hz and greater than 20 kHz with at least a minus 20 dB attenuation. For the requirements, we needed a 6th order Chebyshev bandpass filter, which had the following equation for 3 second-order sections, where the subscript n represents the cascade number. On the left, we have the MATLAB graph of the equivalent circuit and the frequency response. Here again, we have the theoretical equation for a second-order section of a bandpass filter. For our 6th order Chebyshev bandpass filter, we needed 3 of these second-order filters cascaded along with a gain circuit. Below, we have the capacitance values needed for all of the cascaded filters, as well as the GM values, and the gain for the gain circuit. Here we have 3 second-order GMC bandpass filter circuits cascaded together, with the output of each one being taken at the bandpass node, as well as a gain circuit used to amplify the signal. Here we have the simulated result of our bandpass filter from Multisim. As we can see, the stop band attenuation requirements were met. However, the pass band had a ripple of about 5 dB, which was slightly larger than the 1 dB requirement. For the second path, we needed a low-pass filter with the following requirements: a pass band from 0 Hz to 5 Hz and a pass band ripple of 1 dB, and a stop band at 10 Hz with an attenuation of at least minus 20 dB per octave. For this, we obtained a third-order Chebyshev low-pass filter equation from MATLAB that is shown here, as well as the graph from this equation showing the frequency response for the filter.
This is the transfer function of the third-order Chebyshev low-pass filter, which is formed by cascading a first-order low-pass GMC filter and a second-order low-pass GMC filter. These are the values for the capacitances and the transconductance. This is the circuit schematic for the low-pass filter. This is a first-order GMC low-pass filter cascaded with a second-order GMC low-pass filter. This shows the SPICE simulation for the low-pass filter. The filter perfectly cuts off at 5 Hz with a 1 dB ripple, and the stop band attenuation is about 22 dB at 10 Hz.
Now we look at the two-tone test for the bandpass filter to determine the distortion of the bandpass filter. We started at the harmonic frequency of 10 Hz, and we sampled up with our two frequencies being at 20 Hz and 40 Hz. This will give us our distortion, and we found that it was less than negative 40 dB below the primary harmonic for the two-tone test. Now we look at the two-tone test for the low-pass filter. This frequency was sampled at 0.5 Hz. with the two tones being 3 and 3.5 hertz. This gives us a few noise measurements in between to measure off of. We also found this to be negative 40 dB below the primary harmonic.
We had to calculate the signal-to-noise ratio for the bandpass filter. The requirement was 60 dB from the output filter. We plugged the simulation data into this equation and obtained 61.9 decibels, which is above the requirement. We then needed to calculate the signal-to-noise ratio for the low-pass filter. The requirement was again 60 decibels from the output filter. We plugged the simulation data into this equation and obtained 63.6 decibels, which is above the requirement. For area and power, the low-pass filter had an area of 1.15 millimeters squared, and the bandpass filter had an area of 1.02 millimeters squared. This is similar to the area of a mechanical pencil lead. The low-pass filter uses 56.65 nanowatts, and the bandpass filter uses 104 nanowatts. Thank you for watching. We hope you enjoyed the video.